Hello everyone, welcome to all in this PDC lecture series. In this lecture, we'll talk about the transfer function. So let's assume that we have a process in time domain where a small x of t is an input a small y of t is an output. So based on the any fundamental law, we can describe the response of the system by a nth order linear differential equation. So let's assume that after applying the fundamentals laws such as mass balance, energy balance and momentum balance, we get an nth order linear differential equation. So let's assume that after applying the fundamentals laws such as mass balance, energy balance and momentum balance, we get an nth order linear differential equation. So this process is described by a nth order linear differential equation a small a n t n y of dt n plus a n minus 1 d n minus 1 y of dt n minus 1 plus and so on, plus we have a1 d y by dt plus a naught y equal to b small x of t. So let's assume that the process is described by this equation number 1, which is nth order linear ordinary differential equation. So if we change the input x of t, we will get this ordinary differential equation of nth order, and we have to solve this nth order equation so that we can get the response y of t. So let's assume that the coefficient a n is not equal to 0. So in that case, first make this coefficient as 1. So to make this coefficient 1, we have to divide we have to divide all the coefficient by a naught both sides. So by dividing equation 1 A naught, which is the coefficient of y. So finally we will get an by a naught dn y by dt n plus a n minus 1 upon a naught d n minus 1 y dt n minus 1 plus and so on, and here we will get a1 by a naught dy by dt plus y equal to b upon a naught x of t. So this is equation number 2. So equation 2 is the nth order linear differential equation. So for any nth order system or process, we will have n plus 1 system parameters. So let's assume that Pn is an by a naught Pn minus 1 equal to an minus 1 upon a naught and so on, a1 upon a naught equal to P1, and we have Kp equal to B upon A naught. So here we have total n plus 1 system parameters. So this Kp is process gain, and these are other parameters, So this is equation number 3. So for first order system, we will have, for first order system we will have a first order linear differential equation. So here we will have first order linear differential equation. We will have two system parameters, So one will be process gain and the second will be the time constant. So let's assume for a first order system we have a1 dy by dt plus a naught y equal to b x of t. So this is equation number 4. So this equation number 4 represent a first order system. So before finding the system parameters, first we have to make the coefficient of y as 1. So to do so, we have to divide the whole expression by a naught, and so therefore the system parameter, so the process gain Kp will be b upon a naught, and time constant will be a1 upon a naught. So this way we can get these two system parameters for the first order system. Now coming to the second order system. For second order system, the second order system is described by a second order linear differential equation. So it will be described by a second order linear differential equations, and here we will have three. One will be Kp process gain, second will be time constant, and third will be zeta. So we will have three system parameters. So let's assume that the second order system is described by a second order linear differential equation a2 d2y by dt square plus a1 dy by dt plus a naught y equals b small x of t. So let's say this is equation number 6, which represent a second order system. So using this expression, now we can find out these system parameter Kp, tau and zeta from this experiment. So the three system parameters Kp, tau and zeta can be evaluated from equation number 6. So to do so, first divide. So divide equation 6 by a naught. So here again we have to make the coefficient of y as 1. So we will get a2 by a naught d2 y by dt square plus a1 upon a naught dy by dt plus y equal to b upon a naught x of t. So this is equation number 7. So here this will be process gain, this will be tau square, and this will be 2 zeta tau. So from equation number 7, so the three system parameters can be calculated the three system parameters can be calculated as follows. So the tau square will be a2 by a0, 2 zeta tau will be a1 by a0, and process gain kp will be b upon a0. So using this expression, equation number 8, we can get this. So let's say this is 8 point A, this is 8 point B, and this is 8 point C. So we will use these three equations, 8 point A, 8 point B, 8 point C, to find out these three system parameters, tau, zeta and kp. Till now we have explained the order of a system and the system parameters. So now let's find out the transfer function. So to find out the transfer function, we have to transform the ordinary differential equation into S domain. So the transfer function can be defined as g of s equal to y of s upon x of s. It means it's a ratio of output in S domain upon input in S domain. So the transfer function g of s can be defined as y of s upon x of s equal to output in S domain divided by input in S domain, or g of s equal to Laplace transform of small y of t upon Laplace transform of small x of t, and that is equal to y of s, capital Y of s, capital X of s. And this is the definition of Laplace transform, and this is equation number 9. So now let's find the transfer function for first order system. So for first order system, we will have a1 dy by dt plus a0 y equal to b x of t. So now we will transform this differential equation into S domain. So before that, we have to divide both sides by the coefficient of this y, that is a0. So we will get a1 by a0 dy by dt plus y b upon a0 x of t. taking Laplace transform. Taking Laplace transform on both sides, we will get a1 by a naught the Laplace transform of dy by dt plus the Laplace transform of y equal to b upon a naught the Laplace transform of x of t, and this will be a1 by a naught. Here we will get s y of s minus small y at t equal to 0 plus y of s equal to b upon a naught capital X of s. So here we will get, so let's assume that y at 0 equal to small y at 0 equal to 0. So we will have a1 upon a naught s plus 1 y of s equal to b upon a naught x of s. So as we know that this is tau and this is kp, so we can write this as tau s plus 1 y of s equal to kp x of s. So y of s upon x of s will be equal to kp tau s plus 1. So this is the transfer function for first order system, that is kp upon tau s plus 1. So for the first order system, the transfer function is kp upon tau s plus 1. Similarly, we can find the transfer function for second order system. So for second order system, we will have a second order differential equation, and this will be given by a2 b2 y by dt square plus a1 dy by dt plus a naught y equal to b x of t. So again we have to make the coefficient of y as 1 before doing the Laplace transform. So let's divide the whole expression by a naught. We will get a2 by a naught d square y by d t square plus a1 by a naught dy by dt plus y equal to b upon a naught x of t. So now introducing the system parameter. So this is given by tau square, this is given by 2 zeta tau, and this is given by kp. So finally here we will have tau square d square y by dt square plus 2 zeta tau dy by dt plus y equals x of t. So finally we will have tau square d square y by dt square plus 2 zeta tau dy by dt plus y equal to kp x of t. So this is equation number 11. So now we will take the Laplace transform. So now taking the Laplace transform, we will get tau square d square y by dt square plus 2 zeta tau Laplace transform of dy by dt plus Laplace transform of y equal to kp Laplace transform of x. So finally we will get tau square s square capital Y of s minus s small y 0 minus y prime 0 plus 2 zeta tau s capital Y of s minus small y 0 plus the Laplace transform of y equal to capital Y of s, and the Laplace transform of x is capital X of s. So finally we will have, so let's assume that we have the initial condition as 0. So y at 0 will be equal to 0 and first derivative at 0 will be equal to 0. So we will get tau square s square plus 2 zeta tau s plus 1 capital Y of s equal to kp x of s. So the Y of s upon capital X of s will be equal to kp upon tau square s square plus 2 zeta tau s plus 1, and this is the transfer function for second order system, kp upon tau square s square plus 2 zeta tau s plus 1. So the equation number 12 represents the transfer function for second order system. So here we have the transfer function for first order system as well as second order system. So the next now let's discuss the dynamic response of first and second order system. So dynamic response of first and second order system. So now let's discuss the dynamic response of first and second order system. So now let's talk about the step response. So four step response small x of t can be given as a u of t. So let's assume that we have provided a step input of magnitude a to the system. So here we have process which is described by a transfer function g of s, and here we have input x of s and output y of s. So let's discuss first the first order system. So for first order system, g of s equal to kp upon tau s plus 1. And here we have given small x of t equal to a u of t. So now we can take the Laplace transform of small x of t. So we will get the Laplace transform of small x of t, and this will be a by s. So finally we will have capital X of s equal to a upon s, and this is equation number 14. Since we know that the transfer function for any process is given as y of s upon x of s, so from equation 13, y of s will be equal to g of s into x of s. So this will be kp tau s plus 1, and this will be a upon s. So this is a kp s tau s plus 1. So since the coefficient of s is here tau, so we have to make this coefficient as 1. So to do so, we have to divide the whole expression by tau. So finally we will get a kp upon tau s so here we have tau s plus 1. So since we have divided the denominator by tau, so we will get this tau get cancelled. So finally we will have a kp upon tau upon s plus 1 by tau. So now we can express this y of s So now we can express this y of s in terms of c1 upon s plus c2 upon s plus 1 by tau. So where c1 and c2 are the constant which we have to find out. So let's say this is equation number 15. So to find c1, so c1 will be limit s tends to 0 and the denominator of c1 is s times y of s. So here we will have limit s tends to 0 s into y of s, and this y of s is this one. So this y of s is a kp upon tau s plus 1 by tau. So finally we will cancel out this s, and now we will have a kp by tau upon s plus 1 by tau, and this s at 0. So now replace this s with 0. So finally c1 will be equal to a kp. So for c2 we will do the similar operation. So for calculating c2 we have to find out limit s tends to minus 1 upon tau, and the coefficient of c2. So the coefficient of c2 is s plus 1 by tau y of s. So here limit s tends to minus 1 by tau s plus 1 by tau, and y of s is a kp upon tau s plus 1 by tau. So this s plus 1 by tau are getting cancelled, and we will have, so we will have c2 equal to a kp by tau upon s, where s equal to minus 1 upon tau. So a kp upon tau minus 1 upon tau. So c2 will be equal to minus a kp. So from equation number 15, so substitute c1 and c2 into equation 15. So we will get y of s equal to a kp upon s minus a kp s plus 1 by tau. Take inverse Laplace transform. Take inverse Laplace transform, we will get a kp inverse Laplace of 1 by s minus a kp inverse Laplace of 1 by s plus 1 by tau. So this will be small y of t, and this will be a kp, this will be 1, and this a kp e to the power minus t upon tau. So a kp common, and in bracket we will have 1 minus e to the power minus t upon tau. So the small y of t will be equal to this. So for a step input of a magnitude, we will have the response as small y of t equal to a times kp in bracket 1 minus e to the power minus t upon tau, and this will be equation number 17. So equation number 17 will represent equation number 16 will represent. So basically this 17 is equation number 16. So equation number 16 will represent the response of step input. So now let's say one example. We have a transfer function 1 upon 5 s plus 1, and we have given an input of 2 ut. So now we have to find out y of t. Second, what will be the value of y after 4 time constant. So to do this problem, first write the transfer function. So the transfer function is given as 5 s plus 1, and this is y s upon x of s. So this is equation number, let's say 1. The second, we have given small x of t equal to 2 u small u of t. So the input is given as a step input of magnitude 2. So after taking Laplace transform, we will get x of s, and that will be equal to 2 by s. So from 1, the output y of s will be equal to g of s into x of s. So 1 upon 5 s plus 1, 2 by s. So make the coefficient of this s as 1. So to make 1, we have to divide this by 5. So finally we can write y of s equal to 1 by s. So here we will divide the whole expression. So here we have 1 by 5, and this will be s plus 1 by 5. And this will be 2 by 5. So here we can write C1 upon S plus C2 upon S plus 1 by 5. To find out C1, we will use limit S tends to 0. So the coefficient of C1, that is S into y of S. So we will use limit S tends to 0, S, and here we have 2 by 5 upon S plus 1 by 5. So finally SS is cancelled and we have two by 5 S plus 1 by 5, and here S at 0. So now substitute this S at 0. So finally we will get 2 by 5 upon 1 by 5. So we have 2. So this is C1. Similarly, C2 can be calculated as limit S tends to minus 1 by 5. The coefficient of C2, that is S plus 1 by 5 times y of S, and here we will have limit S tends to minus 1 by 5 S plus 1 by 5, and here we have 2 by 5 upon S plus 1 by 5. So finally this S plus 1 by 5, S plus 1 by 5 will cancel out and we will get 2 by 5 upon S, and here we will put S is equal to minus 1 by 5. So finally we will get 2 by 5 upon minus 1 by 5, and that will be minus 2. So C2 is minus 2, C1 is 2. So finally y of S will be equal to 2 by S minus 2 by S plus 1 by 5, or we can get 2 1 minus 2 1 by S minus 1 by S plus 1 by 5. Taking inverse Laplace, we will get small y of t equal to 2 inverse Laplace of 1 by S minus inverse Laplace of 1 upon S plus 1 by 5. So finally small y of t will be equal to 2 1 minus e to the power minus t upon 5. So this is the final response for the step input for a first order system. So if you see, so next we have to find out y at 4 tau, right? So next we have to find out y at 4 tau, and where tau is time constant. So since the transfer function for first order system is given by 1 upon 5 s plus 1, and if we compare this transfer function with the standard transfer function for first order system, so we will get kp equal to 1 and tau equal to 5. So here the time constant is 5, therefore y at 4 tau will be equal to y at 20. So y at 4 into 5, that is 20, and this can be given as twice of 1 minus e to the power minus t upon 5. So therefore y at 4 tau will be equal to 1 minus e to the power minus 20 upon 5, and this will be 1 minus e to the power minus 4. Therefore y at 4 tau will be equal to, so 2 into 1 minus e to the power minus 4. So this is 1.96. This is 1.96.